course. If you got questions about anything, come see me or come see Hope. Either of us are happy to go over things with you. Any questions at all before we get started? Let's chat about our next section that we're going to be discussing. We're going to do this in the next couple of days. This is an extension of what we've been talking about with exponential functions. We're going to do what we refer to as modeling with these things. So you may have heard of things like exponential growth or exponential decay in previous classes or in other classes. So what we're talking about is that kind of same idea here with growing or decaying kind of ideas. So just to remind before we get started in some of these problems, remember when we have an exponential function that looks like y equals a to the x, what were the two basic shapes for those? Up and to the right or down to the right, right? So we had two basic shapes that popped up. One went flat on the left-hand side going up and to the right, and the other one went kind of starting up high and then flattened out as it go to the right. How did we tell the difference between which shape we had?
The base, so it was greater than 1 between 0.
So if the base is greater than 1, we know it went up and to the right. If the base was between 0 and 1, went down and to the right. Now again, I've already used the words exponential growth or exponential decay. Which one do you think, whoops, I guess I didn't really make that get close to the x-axis, did I? Which one do you think represents growth? The left one or the right one? The left one, all right? And the other one we represent decay, all right? So if we've got a base that's bigger than 1, we would expect an exponential growth idea. If we've got a base that's between 0 and 1, we would expect an exponential decay idea, right? Okay. Now, this isn't quite an exponential function because it doesn't have the correct form, but we can make it kind of a stretch or a shrink of an exponential function. Looking at this first example, without going through any of the problems or any of the questions associated with it, looking at that first example, would you expect that to be an exponential growth or an exponential decay? Just looking at the form of it. What's the base? The base is a 3 that we see in there, right? Okay, we got some transformations going on. We'll talk about how that affects things here in a minute. But that base is bigger than 1, right? So we would expect this is talking about a growth, which kind of makes sense when we're talking about population of these things, right? We would hope that the population would grow versus die out, okay? So we would expect kind of an exponential growth idea. Now, remember that when we have any exponential function, the y-intercept was 1, right? For any of those. If I say had y equal 2 times a to the x, or I put a 2 out in front, how would that change your graph? Where would it cross the y-axis now? At 2, right? Because what does that 2 do? It makes a vertical stretch, right? Makes it twice as tall. So if you had a 2a to the x, doesn't matter if it's if a base is bigger than 1 or between 0 and 1, it would then cross the y-axis at a 2, right? Agree with that? There was nothing special about 2, was there? No, wasn't special about 2. So any constant that I had there would make it cross the y-axis there, right? Now, we know that it crosses the y-axis at that point. That corresponds to an x value being plugged in at 0, right? So one of the ways that you'll see this written is, especially if we're doing something in terms of time, like we have in this example we're going to do here in a second, you might see it written this way, where you have an a sub 0, capital A sub 0 times an a to the t. This usually refers to as the initial amount or the amount present at time 0, t equal to 0, okay? And we already said that whatever that constant is out in front, that's what's going to correspond to the y-intercept, which is what corresponds to when you put 0 in for the variable, right? Agree with that? Okay. So again, if we go back to this example, what would be the initial amount of alligators looking at this example? Be the 247, right? Because that's what you get if you put in t equal to 0, right? So this 247 here is the initial amount, even though I didn't ask for that. That's what that 247 represents in this case. Yeah. Does that make sense? Now, notice that we see have a base of 3 here, but of course we got that divided by 3 idea in the exponent. Remember when we do a constant on the inside of a function, that's a horizontal stretch or compression, right? Since we're dividing by 3 here, we would actually stretch it by a factor of 3. I'm not as worried about that, because one of the things that we could do here, instead of writing it this, and I'm not, you don't have to do this, but I'm just saying one of the things we could do here, oops, 3 to the t over 3, is I could, remember when we have one exponent raised to another, we multiply, right? I can actually break this back apart and write this as 247 times 3 to the 1/3 to the t, that way. I still see a base. I still see a base here that's bigger than 1, and it fits this form here, doesn't it? If I write it that way. Okay. So even though we've got something that looks like a vertical, or excuse me, a horizontal compression or a stretch, really I could just rewrite it using our properties of exponents and just make it a base to a variable. Okay. We'll talk a little bit more about that later when we start talking about some general models. Okay. Anyway, let's go back to this idea. This one asks you for what is the tripling time for this population. So what that means, sometimes you'll hear doubling time, tripling time, or half-life if you're doing exponential decay kind of ideas. This is, first it's asking you for a time, right? This means the time it takes for the population to triple in size. That's what tripling time means. It's the time it takes for the population to triple in size, be 3 times as big. Okay? So how might we attack this? Well, what did you tell me the initial population is? The 247, right? If I could spell the word initial, that would be helpful. Oh my goodness, stop moving. The initial population is 247, all right? So triple that, multiply it by 3, it's 741, I think. Yep. Okay. So really what this question is asking you is, when will the population be 741? Okay. So is this looking, when it's asking you when will the population be 741, is this asking you about an input or is it asking you about an output? Well, let me ask it a different way. Is 741 an input or an output? It's an output, right? You put in a time, you get out a population, right? So this is an output, so you're looking for an input, right? So how are we going to solve, what do we need to do to figure out the input that goes with 741? Yeah, we'll solve for t, right? Set it equal to 741 and solve. So you'd have 741 equals 247, 3 times, or 3 to the t over 3. Divide by the 247. We already know what that answer is going to be. It's going to be 3, right? We just did 247 times 3 to get the 741, right? Do we have the same base on both sides? So how do we solve such an equation? The exponents are equal, right? What's the exponent on the left-hand side? It's a 1. So you have 1 equals t over 3, or t is equal to 3, right? Because I'd multiply both sides by 3. And t, what's the units on t? Years, yeah. So this would be t is 3 years. Okay. So every 3 years, what this says is that that's the tripling time. Every 3 years, the population will triple. Okay, that's what that says. What questions do you have? Okay. See if you can do the next part. Similar to that part. See if you can do the next part. So we want when the population is 6669. So that's an output. So we'll set that equal to the 247 times 3 to the t over 3. Yeah. Okay. What you do next? Divided by the 247. Okay. Good. That's a good first step. Get that out in front. Get rid of the thing that's out in front. When you divide 6669 by 247, you get 27. Good. Are you able to get the same base on both sides on this one? Yep, 27 is 3 to the third. And now since you have the same base, yep, 3 equals t over 3, or t equals 9 years. Good. What questions do you have on that one? It's okay? All right. So one of the things that I mentioned here is that notice that we had this kind of scaling factor doing a horizontal stretcher shift, right? Notice that if that over 3 hadn't been there, if you just, let me write it off to the side over here. If you would have just had your f of t equaling 247 times 3 to the t, like that. Notice that your tripling time, when we did that 741 equals 247 times 3 to the t, what would your tripling time be in that case? It would be 1, right? So notice that over 3 is what's stretching out the tripling time, right? So if it were over 4, it would have been 4 years. If it was over 7, it would have been 7 years, kind of idea, right? Agree with that? All right, so let's look at this next one. It says it starts out with a population of 396, and it triples every 27 minutes. Okay? Well, first off, since it says it starts out with 396 bacteria, what do you think you're going to do with that 396? What do you think that represents? Yeah, the initial amount, right? That's going to be the number that's out in front, correct? So your number out in front is going to be 396, right? Since we're talking about things tripling, we're going to use a base of 3. For example, if it were a doubling, what do you think you would use for a base? 2, right? Quadrupling, you would use 4. Good, right? Again, we just said a second ago that if I just had a t here, then your tripling time would be what? If I just had a single t and no coefficient, the tripling time would be 1, right? I want it to be 27, right? So what do you think I need to do with that t to change it from a 1 to a 27? Yeah, divide it over by the 27. Good. Just like what we did in that previous example, right? The reason for that is think about the equation you're trying to solve. You have 3 equals 3 to the t over something, right? Right? What do you need to do to both sides? They need to multiply by the 27, right? That's why we have it in the denominator. Okay. Remember that when we talked about horizontal stretches and compressions, whatever's on the inside kind of makes it do the opposite, right? I want to make the tripling time 27 times as long, so I'm going to divide by the 27, kind of the opposite of it, right? So anyway, this is the equation, the formula that we want. Okay. All right. So now we should be able to answer the next question. It asks you to find the population after an hour and a half. Is that an input or an output? So let's think about our function. We put in a time and get out a population, right? So the 1.5 hours is going to be an input, right? But how did we set up the equation? It was in minutes, right? So what do we need to do with that 1.5 hours? Make it minutes. And how many minutes will that be? 90? Okay, so now how to find the population, what do you do? We want to find f of 90, right? 396 times 3 to the 90 over 27. Now it looks like a good problem for a calculator. Just 15,420. Good. And that'll be bacteria. Is this okay? What questions do you have? Okay, well, let's go on to the next one. All right, so in the previous problems, we said that it was tripling time, we have a base of 3. We're doubling time, you use a base of 2. If we're quadrupling, you use a base of 4, and so on down the line, right? Mm-hmm. This problem is saying something about half-life, right? So a half-life, just as a definition here, half-life means this is the time until 1/2 of the initial amount is remaining. Okay? So half-life means literally 1/2 of that. Okay? So if doubling time, we'd use a base of 2. Tripling time, we use a base of 3. If we're saying half-life, what base would you use, do you think? 1/2. Yep, good. So we'll start with, they use an A of t here rather than an F. We'll use 1/2 to some power. Now, I may need to do an adjustment on my t, right? We'll talk about that in a second. But I'm going to do 1/2 to some power. Okay? Again, though, if I put 0 in for t, that constant out in front is going to represent the amount at time 0. In this case, they don't tell you what the amount of time 0 is. So we'll just leave that as an a sub 0. That we'll use that in the next part. Okay? But let's talk about what we need to do to that t in the exponent. Before we said if we didn't have anything that we divided out by, the tripling time would have been 1, right? It's the same idea here. If I don't divide that t by anything, the half-life would have to be 1, right? Is that what we want? Do we want a half-life of 1? No, we want a half-life of what? 12.3. So what do you think we want to do with that t to change the half-life of 1 to a half-life of 12.3? Yeah, divided by the 12.3. Good. We can write it so we can read it. That would be very helpful. 3. Okay. So far, so good? So that's the first part, right? Do we understand why we're dividing by the 12.3, by the way? All right. Because again, if you had 1/2 equals 1/2 to the t, then your t would be 1, right? And that would give you your half-life of 1. I need to adjust this to stretch out the half-life from 1 to 12.3. Remember, to do a horizontal stretch, you have to divide by that number, right? It's the opposite, right? For vertical, you multiply. For horizontal, you divide. Okay? All right. Okay, so let's look at the part B. How much of a 5-gram sample would remain after 5 years? Okay? Now that it says a 5-gram sample, how do you think you're going to use that information?
Starting a base 5?
So if we have a 5-gram sample, that's telling you that you're going to start with that, right? So what value is that going to be? The initial value, that a sub 0, right? So now we know our function is 5 times 1/2 to the t over 12.3. Right? Okay. Now, what's the problem asking you? How much would remain after 5 years? Is that 5 years referred to an input or an output? Input, right? So we'll plug that in for t. Oops. Put it in for t, I said. That looks like a good job for a calculator, doesn't it? Say again. Okay. 3.772 grams. Would you do anything different for part B? Well, besides change the number. Or is part B basically the same problem? It'd be the same problem, right? So for part B, C, you would do A of 7 is 5 times 1/2 to the 7 divided by 12.3. Wait, 370? Okay. Great. Those parts make sense? I don't have it on the paper, but let me ask you a different question. What if I asked you, when will there be 2 grams left? Yep, good. This is an output, right? Remember, you're putting in a time and getting out a number of grams, right? So in this case, you would set the function equal to 2. Right? The first thing you would do here would be what? I need to divide by the 5, right? I'd get 0.4 equals 1/2 to the t over 12.3. Now this one's going to be hard to try to get the same base on both sides. Don't be fooled by the 4, okay? Because that's 4 over 10, right? It's 4/10. Okay. So if I can't get the base on both sides easily, how do we get the variable out of the exponent?
Yeah.
Yeah, take the log, right? Either log or ln, doesn't matter which one, right? You can do either, okay? I'll do natural log personally. Because again, that allows you to do what? We put the exponent down in front, right? If you get nothing else out of what we've talked about with logarithms, get that if you have a variable up in the exponent, you want to take the natural log to get it down, okay? That's honestly the biggest thing that you can get out of doing logs is if I've got a variable up in my exponent, I take a log to bring it down to where I can deal with it. Okay. Now I need to get t all by itself. What operations do we need to do here to get t all by itself? And I got to multiply the 12.3. What else do I need to do? Because this is multiplied here. What else do we need to do to get t all by itself? Multiply by 12/3 to get out of the denominator. What do I need to do to get this? Yeah, I got to divide by it, right? So if it were a 3t, you would divide by 3, right? Okay. So now this looks like a good calculator problem. It's like a good thing to put in your calculator. You say, wait, 259? Is that what you said?
Yes.
Okay. And that'll be in years since they told us the half-life was, or the time was measured in a year. What questions do you have on this one? I'm going to leave the next one for practice. I want to do the following one here. And then we'll leave some more. We'll leave some more of these for next time. This next one's a little bit more general. So in the previous problems, we were told things about tripling time or half-life. This book is a little bit more general, and it's a little bit more indicative of the types of problems you would do if you were trying to model data. So what we're trying to do, right? If you're doing things either from a business sense or a scientific sense, you're going to get data and you're going to try to model what goes on. That's kind of the point, right? Exponential functions are used to model things that are growing. So they're used to do population growth. They're used to do stock prices, right? There's all sorts of different things that exponential functions are used in, both in business, in economics, or in biology or chemistry or physics, okay? Lots and lots of applications to exponential functions, right? But usually, again, you're going to be given data. You're not going to be told, oh, I know what the half-life is, or oh, I know what the tripling time is, right? So I don't necessarily know what base to use to start with, okay? This is one of those situations. It tells you that you start with 134 rabbits. In 3 years, it's increased to 1,072. Okay? They didn't tell us anything about doubling time or tripling time or half-lives or anything along those lines, right? So in those instances, we start with a more general exponential function model, and usually we use that natural exponential function as a base. So we use e for our base. Again, nothing really special about e except that we refer to that one as the natural exponential function. It pops up. You could use any base to start with, but again, the two natural ones you would use from a computational standpoint would be e or 10, because those are the buttons you have in your calculator. Okay? We'll use e. So our general model will be a of t equals that initial amount, that's still the initial amount, that a sub 0. We'll do e and then a constant times t. Okay? Just like what we talked about with the half-life or the tripling time, we had to do that scale to stretch it appropriately. That's what that k is doing. That k will either stretch or compress depending on the scenario, okay? So in all of these problems that you're going to fit this general exponential model to, you've got two pieces of information to figure out. You need to figure out the initial amount, and you need to figure out what the k value is, okay? Well, again, the initial amount here is given to you, isn't it? It says, to control vegetation, 134 rabbits are released. If we consider that the time when they're released to be time 0, what's your a sub 0 going to be? 134, right? So this 134 rabbits part right here, this is telling you your initial amount. So the first thing I have is 134 e to the kt. So I have my a sub 0. I still need to figure out k. Okay? That's the next piece of information we're given. After 3 years, we've increased to 1,072. Okay? Does your 3 years here, is that going to correspond to an input or an output? Input, right? Because that's the time, right? The 1,072 is going to be an output. So what this says is that if you put in 3, you're supposed to get out 1,072, right? So we put in 3. According to the function, that should be 134 e to the 3t. That's supposed to equal 1,072. Oh, not t. 3. We put in 3 for t. That should be 3k. Sorry. The whole point of this is that we try to figure out what the k is. Okay, sorry about that. Okay. What do we need to do first? Divide. E to the 3k will be 1,072 divided by 134. I have a variable to solve for that's up in the exponent. What's our big technique for getting that out of the exponent? Log, right? Now in this case, since I used e for my base, I really do want to use natural log because they undo each other, right? So if we have natural log of e to the 3k equals natural log of 1,072 over 134. Natural log and e cancel each other out. So what are we left with on the right left-hand side? 3k. And then to solve for k, what do we need to do? Divide. Good. I'm going to write it as multiplication as by 1/3, just so it looks a little bit nicer up on the screen. And did you get a decimal approximation for that one? Okay.
Is there a reason why we left this in a fraction instead of just simple?
You can put it as a decimal if you want to. I just left it.
It does simplify to 8.
I simplified to 8?
Yeah.
Oh, okay. That's fine. Generally they won't simplify that nicely. Yeah. Yeah. That was why I really left it as a fraction. I didn't recognize it was 8 times as big. Sorry.
I'll get it.
Yeah. You could have absolutely written it as 8. What do we get for a value for that one? Six, 9, 3? Okay. Good. Ish. Okay. Whenever you're doing the problems, it's fine to write the rounded on your paper, but I would keep as many decimal places as you can in your calculator when you do the computations. It just makes them a little bit more accurate. Okay. Now let's see what the problem asked us. It says, assuming exponential growth, what will the population be after another 6 months? Now again, is that referring to an input or an output? The 6 month, that additional 6 months is an input, right? And we're trying to figure out the output. Now it says additional 6 months. What number do you want to plug in as your input? Okay, so 0.5 is good because I need it in years, right, rather than months. But it says an additional 6 months. 3.5. Good. Yeah, I need to do 3.5, right? We just used the 3 years, and then it says an additional 6 months. So we need to put in 3.5. Good. So you'll have 3.5. So you'll do 134, and I wrote a 7. 134 e to the k value was about 0.693. You should have that in your calculator, so you can use your previous answer button. And then times 3.5. Now, you may not know what the value is off the top of your head, but what number does it definitely need to be bigger than here? When we're done for the output, it better be bigger than which number? It better be bigger than that 1072, right? Things are growing, right? If I put in a bigger number for t, I better get a bigger number out. So things are growing. What do you get about here? 515, is that what it said? Okay. And that's rabbits in this case. What questions do you have? Is okay? All right. We'll do more of these examples on Friday. Okay. Not a lot of time to do another example, so we'll just go ahead and do more of these examples on Friday. Have a good one. We'll see you then.